Okay, in this lecture, let us discuss convolution in time and convolution in S domain, and also how to take the Laplace transform of a periodic signal or periodic function. So, let me start with the convolution time domain. Okay, so this is sometimes referred to as a real convolution. This is said to be a real convolution in the sense that we are carrying out this convolution in time domain, which is a real variable. Let us say I have two signal x of t and h of t. The convolution of x of t with h of t is like this, and here the convolution is with respect to the variable t, and this variable t is a real quantity, okay, real number. After all, time is a real, right? So, this is called a real convolution. Sometimes people will call real convolution. Okay, not in the transform domain which is a complex variable. Okay, so this is a real convolution. Now, if you recall, x of t convolved with h of t is equal to integral of x of tau h of t minus tau and d tau, and the limit is, let us say, minus infinity to plus infinity. This both are equivalent. Okay, either you can write like this or like this. In fact, you can write x of t minus tau and h of tau and d tau. Either way you can write. Both are one and the same. And the limit is, as I said, it is from minus infinity to plus infinity in general case. In case if you consider a causal functions where x of t is equal to 0 for t less than 0 and h of t is equal to 0 for t less than 0 causal functions, then the integration starts from 0 onwards. Okay. Let us say if you have an impulse at exactly at 0 minus and 0 plus, in case if you have an impulse at t equals to 0, then you start the integration from, instead of 0 to infinity, you start from 0 minus to infinity, that is it. Okay. X of tau h of t minus tau d tau, or you can write x of tau h of t minus tau and d tau. Either you can start from 0 minus or 0 plus. If you have an impulse at the origin, then you must put a 0 minus. Therefore, x of t convolved with h of t is equal to 0 minus to infinity x of tau h of t minus tau and d tau. Now, the axis is integration axis is with respect to tau, and this is 0, and let us say this point is t, right. When in this range, what is the tau value? Tau is less than t, and in this range, what is the tau value? Tau is greater than t. Now, in this h of t minus tau, if tau is greater than t, then what will happen? It becomes negative. So, we said for a negative values of time it is 0, right. H of t is equal to 0 for negative values of time. Sorry, both x of t is equal to 0 for when I say t less than 0, that means what? Negative values of t. Similarly, h of t is equal to 0 means 0 for t less than 0 means negative values of t. So, now in this expression, when you cross this point t in the integration, you see you start the integration from this point, let us say here 0 minus, you keep on do the integration, okay, and you come to the point where t, and up to this no problem. The moment you cross the t point, then afterwards what happens? your tau value will be greater than t, because you are integrating with respect to tau. So when tau greater than t, in this case let us say t is equal to let us say 20 seconds, and when tau becomes 21 second, then what will happen? You will get a h of 20 minus 21 seconds, which is h of minus 1 second. What is h of minus 1 second? It is 0. Therefore, no need to do the integration up to infinity. Okay, so what I am saying is no need to do the integration up to infinity. Where did I write? Yeah, so no need to do the integration up to infinity. This one. So do the integration up to t, that is enough. Therefore, integral of 0 minus to t x of tau h of t minus tau d tau. So your convolved output is x of t convolved with the h of t is equal to 0 minus 2t x of tau h of t minus tau d tau. Now let us try to find the Laplace transform of this on both sides. So Laplace transform of x of t convolved with h of t is equal to integral of single side Laplace transform 0 minus to infinity, then substitute this guy, integral of 0 minus to t x of tau h of t minus tau d tau multiplied by e to the minus st and dt, right? And then what will you do? Interchange the integration. Okay, so I'd like to do the integration first with reference to tau, and then later on you do the integration with reference to t. So separate these two things, 0 minus to infinity e to the, because I want to do with respect to tau, therefore e power minus st is constant, then dt, and the limit is 0 minus tau equals 0 minus 2, it is capital small t x of tau h of t minus tau and d tau. Okay, now suppose if I introduce u of t minus tau, then the limit I can bring up to infinity. So the same expression 0 minus to infinity e to the minus st dt, and then tau equals 0 minus to infinity x of tau h of t minus tau u of t minus tau. Anyway, that value is going to be 0 after t greater than 0, t greater than tau. Okay, so and d tau I can write like this. So because of this introduction of your u of t minus tau, this upper limit becomes infinity now. So I want to write in the standard form, that's why I introduced this u of t minus tau, right? When tau exceeds t, then this integral becomes 0. So this is one and the same, both are same because of this u of t minus tau. So instead of having t, the upper limit is t, I can replace by infinity with the help of this u of t minus tau. Okay, so I introduced the symbol u of t minus tau. I may as well take the limit of integration of tau from 0 minus to infinity. So to ensure that the same integral is valid even here also, see, let us say this is 1 and this is 2, both are one and the same. The value of the two integrals are the same. Okay, so here I introduced purposely this u of t minus tau and took the limit up to infinity, because the value of u of t minus tau is equal to 0 for tau greater than t. The reason why I did this is because we would like to relate them to the Laplace integrals, that is why. Okay, so now See, we introduced purposely this kind of changing. Okay, so I have introduced this u of t minus tau deliberately. Now again you interchange the order of integration like as what we had in originally. You do the integration with respect to t first. So this is t equals 0 minus. So integral of tau equals 0 minus to infinity, then x of tau you can bring it down here, d tau, interchanging, then integral of t equals 0 minus to infinity, then h of t minus tau e to the minus st, and then dt. I am sorry, where is u of t minus tau? U of t minus tau, and then what is it? dt. Now what is this? This is the Laplace transform of the delayed function, right? See, if x of t has Laplace transform x of s, then x of t minus tau has the Laplace transform of e to the power of minus tau s times x of s. Similarly, if h of t u of t has the Laplace transform of h of s, then h of t minus tau times u of t minus tau has the Laplace transform of h of s times e to the minus tau s. So this whole thing is delayed functions Laplace transform. Okay, Laplace transform of the delayed function h of t. Okay, therefore that is going to be tau equals 0 minus to infinity x of tau, this thing, d tau multiplied by h of s, okay, that is times e to the minus tau s, or you can put s tau, not an issue, and that's it. Now again rearrange this, then tau equals 0 to infinity, then you put h of s commonly outside, h of s integral of x of tau e to the minus s tau and d tau. If you don't like this tau, then you can replace by x of t e to the minus st and dt, and again the limit is minus 0 minus to infinity. And don't you see, this is precisely the definition of the Laplace transform of x of t. So this is x of s. So h of s times x of s. What is there on the left hand side? The Laplace transform of convolution of x of t with the h of t. Therefore Laplace transform of x of t convolved with the h of t. That's it. Therefore in the time domain you have convolution, but in the frequency domain it becomes multiplication. Okay, so the convolution of two time functions has the product of the two corresponding Laplace transforms. So this is the important result. Convolution in the time domain corresponds to multiplication of their respective transforms, Laplace transforms, in the frequency domain or in the complex frequency domain. So this is quite neat. This is a rule which will be useful for our work. As I said, in system studies where the system impulse response is h of t and the input is x of t, and you would like to find out what is y of t. So in the time domain it is convolution, in the frequency domain it is very easy to find out. Okay, to find out the response for an arbitrary signal. X of t is an arbitrary function of time. So all we have to do is Laplace transform of output will turn out to be the product of the Laplace transforms of the impulse response and the Laplace transforms of the input function x of t. Let me take an example. Suppose I have 1 divided by s plus 1 times s plus 2, then we can split this up as 1 divided by s plus 1 times 1 divided by s plus 2. Okay, now let me call this is x of s, and this one let me call h of s. Okay, now what is 1 by s plus 1? If you take inverse Laplace transform, e power minus t u of t, and 1 by s plus 2 if you take inverse Laplace transform ILT, then e power minus 2t times u of t. So the product of these two Laplace transforms must be correspond to the convolution of these two time functions h of t and x of t. So in the time domain, x of t convolved with the h of t. That means integral of 0 to t, then x of tau, h of t minus tau, and d tau, right. So integral of 0 to t, then what is x of tau? X of tau is e to the minus tau u of tau, h of t minus tau is e to the minus of t minus tau u of t minus tau d tau. The time domain convolution I am working on now. So now in the range of integration, when tau goes from 0 to t, then u of t is equal to 1, and this guy also equal to 1. No problem as far as the limit is concerned. Okay. Therefore, 0 to t, e to the minus tau, e to the minus t plus e to the plus tau, and d tau. I am sorry, I forgot 2 here. I think there will be 2 here. Okay, this is minus 2t. I am sorry, let me rewrite properly. This is 2 times t minus tau, and here e to the minus 2t, e to the plus 2 tau. Then the integration is with reference to tau. Therefore, you can pull out of the integration this guy, e to the minus 2t, 0 to t, and if you combine these two guys, e to the tau times d tau. So this is e to the 2t, and the limit is e to the tau and 0 to t. Now substitute the limit, e to the minus 2t, e to the t minus 1. Now multiply inside, this becomes e to the minus t minus e to the minus 2t, where tau greater than or equal to 0. This is what? X of t convolved with the h of t. So this is what we got in the time domain. Now we want to prove this property once again in the frequency domain. Okay. Now we wanted to illustrate this as an application of the convolution theorem. You can get at this result even simply by considering this by making partial fraction expansion, like the frequency domain also you can prove this times s plus 2. You can make partial fractions. So after that you will get 1 over s plus 1 minus 1 over s plus 2. So what is the inverse Laplace transform of this? This is going to be e to the minus t minus e to the minus 2t. In one step you can get the answer, where t greater than or equal to 0. So no need to do this kind of integration and all. Straight away what you do, you take the partial fraction and then you can find the inverse Laplace transform. So both agrees. In the time domain convolution, this is the answer. In the frequency domain, it is multiplication. The multiplication, if you take inverse Laplace transform, you will get again the same answer. That is what we want to show in this example. So we have seen the convolution in time domain corresponds to multiplication of the respective Laplace transforms in the frequency domain. As a dual rule, we have convolution in complex domain, convolution in the S domain. So now let us move on to this. Convolution in S domain. I think this is property number 12. This one is, I think, 11. Okay. So this is called a complex convolution. The previous one is called a real convolution, and this is also called a complex convolution. Why is it called a complex convolution? I will just mention this rule and then we will come to this point. In the time domain, you have x of t multiplied by h of t. In the frequency domain, you will have x of s convolved with h of s. Now the convolution is with reference to what? S parameter. What is S? S is a complex quantity. Therefore, this is called a complex convolution. So this is going to be 1 over 2 pi j integral of c minus j omega to c plus j omega, then x of z times g of s minus z times dz, complex convolution. So you do an integration of the product x of z and g of s minus z, and z is a running variable here. And therefore, this entire integral will be a function of s, and that would be the Laplace transform of the product of these two guys. Sorry, already put a double arrow mark. So whatever you get, that will be the Laplace Laplace transform of x of t and y of t is equal to some function of s. That's it. Finally, you'll get it. Some function. You can work on it. Okay. So let me stop this property at this point, because we will not use this property much. So maybe if you are interested in, you can prove this property on your own. Okay. So the proof is straightforward. You can do it. The next property is periodic function of time. Suppose if you have periodic function of time, then in fact what we can say is, instead of saying periodic function of time, let me say Laplace transformation of so this is 13th property, Laplace transformation of periodic function. Suppose I have a periodic functions of time which is given by like this. I have the function like this, it keep on repeats like this. Okay, let's say this is t naught and 2 t naught, 3 t naught, and so on and so forth, x of t. Now the question is, what is the Laplace transform of this guy? By the way, x of t is periodic function with period t naught. Now to address this problem, what we do is, we will consider only a single pulse. Let's say this is t naught. Now the next question is, how do you get this pulse? Let's say this is my x1 of t and x of t. Now the question is, how do you get x1 of t from x of t? That is the question. How do you get it? It's quite straightforward. What you do, you take a gate pulse. See, you have a function like this. It is keep on repeating t naught to t naught like this. You take a square pulse like this. The magnitude is 1 and this duration is t naught. And the rest of the place, this all places it is 0, right? It is 0. You multiply these two guys. Let's say this is x1 of t and this one. By the way, what is this square pulse? This square pulse is u of t minus u of delayed by t naught. That's it. That gate pulses. Then multiply this and that. Then what will you get? You will get this first pulse alone, and then afterwards everything becomes 0, because you are multiplying with a 0 value. Okay. So this is t naught. Therefore, this is going to be your x1 of t is equal to x of t multiplied by u of t minus u of t minus capital T naught. So, you take a single pulse, the variation of the x of t over one particular period only. Okay. So, this period only. If you know the Laplace transform of this pulse, you can find the Laplace transform easily. Okay. Now, what we do is, you have x1 of t. Let us say x1 of t has the Laplace transform x1 of s, a single pulse. Now, what is the Laplace transform of x of t? Just one second. That's okay. This is okay. Now, from this, if you take Laplace transform, then okay, let it be okay, if you take Laplace transform, then this is x1 of s. Now, if you consider second pulse, let us say this pulse alone. What is this pulse? Second pulse. Let me call x2 of t. What is the Laplace transform of x2 of t? x2 of t, if you take Laplace transform, then you will get x2 of s. But x2 of t is related with x1 of t as x1 of t minus capital T naught, right. So, therefore, if you take again Laplace transform on both sides, like this. Now, you take the third pulse in the same fashion. Let me say this is x3 of t. What is x3 of t? x3 of t is x1 of t minus 2 times delayed version. So, therefore, this is going to be, if you take Laplace transform on both sides, x3 of s is equal to x1 of s e to the minus 2 times t naught. Okay. So, therefore, your x1 of t, this is my, one second, hold on. This is x of t, I am sorry. Fine. So, I have x of t here, and this is x1 of t, x2 of t, x3 of t, and so on. Therefore, I can write x of t is equal to x1 of t plus x2 of t plus x3 of t, and so on so forth. Why? X of t is like this. Now, x1 of t is like this, x2 of t is like this, x3 of t is like this, x4 of t is like this. Let me draw it properly. So, x1 of t, x2 of t, x3 of t, x4 of t. And so on. Therefore, if I add all these guys, it keep on goes, you will get back your x of t. That is what I wrote here. Now, you take the Laplace transform on both sides. So, what will you have? Then x of s is equal to x1 of s plus x2 of s plus x3 of s, and so on so forth. So, x1 of s plus x2 of s is, again if you look at here, what is x2 of s? x1 of s times e to the minus s naught. So, x1 of s e to the minus s t naught. What is x2 of s? Again it is x1 of s e to the minus 2 s t naught. I forgot s here, okay, 2 ts. Okay, so this keep on goes e to the minus 3 times s t naught plus and so on so forth. Now what you do? You take a x1 of s commonly outside, then 1 plus e to the minus s t naught plus e to the minus 2 s t naught plus keep on goes. So this is x1 of s divided by what? 1 minus e to the minus t naught s. So if you have a periodic function of time and if you want to find out the Laplace transform, all you need to do is consider the Laplace transform over one period. You take one pulse over one period 0 to t naught. Let us call this is x1 of s and find the Laplace transform of this. The moment you find the Laplace transform, then your job is over. Okay, so that Laplace transform x of s divided by 1 minus e to the minus t naught s, that's it. So this is how you find the Laplace transform of a periodic function of time. Okay, here t naught is the period of the signal. Okay, period of the periodic signal. Okay, so let me stop at this point. Thank you very much.